Okay. Hello, everyone. Good afternoon, and welcome to our weekly astronomy seminar from the Astronomy Department of the University of São Paulo. Today we have the pleasure of receiving Dr. Anke Arentsen from the Observatoire Astronomique de Strasbourg. Sorry, I don't speak French. She will talk about the galactic archaeology with the oldest stars in the Milky Way. So thank you very much, Dr. Anke, for accepting our invitation. And for those who don't know, Dr. Anke has studied astronomy at the Captain Institute in Groningen, after which she moved to Leibniz Institute for Astrophysics in Potsdam for her PhD. And she's currently a postdoctoral researcher at the Observatoire Astronomique de Strasbourg, and she searches for and studies the oldest stars in the Milky Way to learn about our galaxy's ancient history and the early universe. Before we start, I'll ask for everyone except sorry, it's hard today, except the speaker to turn off your cameras and microphones in order to avoid unwanted noises and interruptions. All the questions will be addressed to Dr. Anke at the end of her presentation. It is valid for both YouTube and Google Meet questions. Okay, so thank you very much. You can start.
Okay, yeah, thank you very much for the invitation. It's a great pleasure to be here, and I look forward to sharing with you about my work. And you should be seeing my slides now.
Yes, we see.
Perfect. Okay. Yeah. So my topic will be galactic archaeology with the oldest stars in the Milky Way, and this work has been done in collaboration with many people at my PhD institute and my current institute. And yeah, so some of these are shown here. Elsa Starkenberg was my PhD supervisor, and Nicolas Martin, and they are leading together a survey called the Pristine Survey, which I will be mentioning more throughout the talk. So why galactic archaeology with the oldest stars? So stars are really great messengers from the past. So here's a schematic history of the universe, with the Big Bang at the beginning, and then a time where there is no stars, and then you have the very first stars forming. And these stars were likely really massive and exploded very quickly, so they wouldn't survive until the present day. But then the next generation of stars can form small stars that survive until today. So then you have the smallest galaxies and clusters forming, and they're merging and building bigger and bigger galaxies until we have galaxies like the Milky Way today. So some of the stars that formed really early in the universe are still present in the Milky Way today. And if we can find them, then we have really unique probes of the early universe. So how can we recognize these stars? So the early universe is made largely of only hydrogen and helium and a little bit of lithium. So the very first stars formed from that material, and then they exploded, and the first heavier elements get released into the interstellar medium. So the stars that form from this material have very low metal content, so they're really metal poor. And then over time, you have increasing metallicity throughout the universe until you have stars today, like the sun. So we can use the metallicity roughly as a probe for the age of the stars. And we can use these stars, the very old stars, to study the properties of the first stars based on the chemical abundances, and also how the Milky Way formed. If we have a lot of these stars and seeing how they move or where they are, what their properties are, we can learn about the building blocks of the Milky Way. So when I talk about metallicity of stars, I'm employing the typical scale that we use for stellar physics. It's a logarithmic scale that is relative iron over hydrogen abundance. And then the sun in this scale is at 0. And most of the stars in the Milky Way, so in the disk and the bulge, they're in this range around the sun, metal poor, so 10 times less than the sun, and some more metal rich. So this is most of the stars in the Milky Way, and most of these stars are in the disk and the bulge of the Milky Way. But then when we go to lower metallicities, we have the very metal poor stars and the extremely metal poor stars. So this is only about 1% of the stars in the Milky Way, and these are mostly in the halo of the Milky Way. But then we can go even lower. We can go to the ultra hyper mega metal poor stars, and these are the really rare remnants of the first stars. And so currently there's only about 40 stars known with metallicities below -4, so 10,000 times less elements than the sun. And these are the rare remnants of the first stars that can really tell us something about the supernovae that were occurring after the first stars, for example. So in this talk, I'll focus on the metal poor stars, and there's different ranges of metal poor stars, typically starting around -1.5 or so. And I have two main topics: so metal poor stars in the inner regions of the Milky Way, and a special kind of metal poor star, which is called the carbon enhanced metal poor star. And I'll explain a bit more about that later in the talk. So when we study the metal poor Milky Way, we know that the halo is on average the most metal poor. So we typically have this big halo that is all throughout the Milky Way, but we only study the part that is close to us. So we are here in the disk, and we typically look out of the disk to study the halo, because that's the easiest place to access the halo. But when you do this, you're actually missing the central region of the galactic halo, which is actually its most dense part. But there's good reasons that we're doing this, because it's challenging to observe through the dust towards the inner galaxy. And also most of the stars in the inner region are actually quite metal rich. So here is a metallicity distribution of a typical galactic bulge survey, an inner galaxy survey. And we can see it peaks between +0.5 and about -1. So these are most of the stars in this region. And there's only a really small percentage of very metal poor stars, so below metallicities of -2. So, but why would you want to look in that region still, despite the challenges? Well, actually, we know from simulations that the oldest metal poor stars are very centrally concentrated in the Milky Way. So here's an image from a Milky Way type simulation, color-coded by the fraction of old metal poor stars. So metal poor stars that were born in the first 0.8 gigayears of the universe. And we can see in the outer halo, so 20 to 60 kiloparsec, we have this dark blue color, but also in the inner few kiloparsecs. There's a really high density of these really old metal poor stars. And this is similar seen in other simulations. So that's a really good reason to look at the inner galaxy. Both the highest density of the halo is there, and also we expect the oldest stars to be in this region. And if we study the metal poor stars, we can start asking and answering questions of what the nature is of the metal poor stars in the inner galaxy, and what kind of building blocks contributed to the galactic halo and to the different regions of the galactic halo. And then finally, we can ask ourselves what we can learn about the first stars and the first galaxies from these really metal poor stars in different galactic environments, which were likely born in different environments in the early universe. So there's very good reasons to study the metal poor inner galaxy. And there's actually quite a bit of recent work on spectroscopic observations of the metal poor stars in the inner galaxy, but usually they're relatively small samples, so you can do only limited things with them. And you need a very efficient pre-selection method, because what you want to do is you want to find the metal poor hay in the very metal-rich needle stack that is the galactic bulge. You need a very efficient hay detector, so to say. So one way to do this is using metallicity-sensitive photometry. For example, from the Pristine survey, which I think Nicolas Martin introduced in the same seminar a few weeks ago, but I'll introduce it again. So here's a color diagram where on the y-axis there's this term calcium HK. And this is a narrowband filter centered on the calcium H and K lines. And this is very sensitive to the metallicity. And you can see here the color is stars of different spectroscopic metallicities that we know of. And we can see that they very nicely separate the really metal poor stars in blue from the more metal rich stars. So we can use this photometry to very efficiently pre-select and then follow up only those interesting stars with spectroscopy. So here is the filter curve in gray versus the wavelength for spectra of typical giants with different metallicities. So -2, -3, -4. And you can see that these strong calcium H&K lines, they change with the metallicity. And they change the flux that goes through this filter, which gives you the metallicity sensitivity. So the Pristine survey is using this filter and surveying the northern sky. And this is an old footprint, and there's currently more than 7,000 square degrees of this metallicity sensitive photometry, and it's still increasing. And in this talk, I want to focus on this inner region. So the Pristine Inner Galaxy Survey, or PIGS, which is a survey that I started developing during my PhD thesis and have been leading since then, and really developing, trying to find the most metal poor stars in the inner region. So that was the general introduction. And then now I'd like to go into two of them, the two main topics of the talk. First is the PIGS, the Pristine Inner Galaxy Survey, a bit more details about the survey and what we can learn about the kinematics of metal poor stars in the inner galaxy. And then the second topic is on these carbon enhanced metal poor stars, both in PIGS and the rest of the halo. And I'll finish with some conclusions. So I already told you about the photometry in the Pristine Inner Galaxy Survey, but we also have spectroscopic follow-up. And we use the AAT, AA omega plus 2DF multi-object spectroscopy instrument to very efficiently get a lot of stars observed throughout our footprint. And these are shown here. So we have the galactic plane here at the latitude of 0 with very, very high dust extinction. So we're staying away from that region because it's just too difficult to do a good selection there. But in the kind of outer regions of the bulge, we've collected about 12,000 spectra of metal poor candidates, and simultaneously low resolution spectra in the optical part, and a bit higher resolution around the calcium triplet. And we can use these spectra to get the stellar parameters, so temperature and also carbon abundances. And then from the calcium triplet spectra, we also get really good radial velocities. So we can start probing how these stars are moving. So how does the metallicity distribution in PIGS compare to typical bulge surveys? So here I'm showing the relative number of stars at a given metallicity in two different surveys looking at the inner galaxy. So we have Apogee, which is a bit closer to the plane, which is why it's a bit more metal rich. And then Argos, and we can see these have almost all of their stars in the higher metallicity range. And then on the bottom panel, I'm showing the absolute number of very metal poor stars, so below these metallicities of -2. We can see that there's very small numbers in these typical surveys. So then there has been the first really focused metal poor bulge survey, which is the EMBLA survey, using a similar filter to the Pristine filter, here the SkyMapper V filter. It's a bit wider, but it also covers these the calcium H&K line. So it's also sensitive to metallicity. And they've been really good at finding the first large sample of metal poor stars and very metal poor stars in the inner galaxy. So they focused mostly on a small number of stars, following it up with high resolution spectroscopy, and they have been published in these papers. So then PIGS is even more metal poor. So here in green, I'm now showing the PIGS distribution, which we can see really starts to pick up after -4.2 or so, and has almost all the stars there, and actually almost 2,000 very metal poor stars. So this is the largest sample of metal poor stars in the inner galaxy to date. And we can really start using this to study the properties of this metal poor population. So a bit on the background about kinematics in the inner galaxy. So here you can see an artist impression of the Milky Way. And I like this artist impression because of the way the bulge is represented. So here you can see it has kind of this peanut shape, which is called the boxy peanut shaped bulge, or the BP bulge in the Milky Way. And this component likely formed from the galactic disk, from instabilities in the galactic disk, and it puffed up. And we can see this by the way these stars are rotating. So here's a work from some years ago, comparing data with different models. The galactic longitude is here and the mean velocity is on this axis. And we can see that it's rotating. Part of it's coming towards us and part is going away. And this is a signature of a cylindrical rotation of this boxy peanut component. So then there's a question, there has been a question for a long time, whether there's also a classical or a pressure supported component of the bulge in the inner galaxy. And the observations of typical metal-rich stars show here again the galactic longitude and now the velocity dispersion, and different models with different masses of classical bulges. And we can see this blue one has a very large classical bulge, and it doesn't fit with the data. The velocity dispersion is too low. So there cannot be a very large classical bulge, even if there is even one. But this is again for mostly the metal-rich stars. And we don't really know what's happening for the more metal poor. Then finally, not finally, but there can also be leftovers from other leftovers from the disk, or we're looking through the disk, so you get some contamination. And then finally, we also have the extension of the galactic halo. And actually the halo has its highest density, although the density of the metal-rich boxy peanut bulge is still a lot higher than the halo in this region. So it's a very complicated region with all these different components. And especially at the metalpoor tail, we don't really know yet what's happening and which component these stars belong to. So I show these curves of the kinematics, which are shown again here, and now they're split up by metallicity from the Argos survey. So we again have the galactic longitude versus the velocity. And we can see in these top panels that with decreasing metallicity, these curves actually look the same, which means that these all appear to be roughly of a similar population or a similar origin. But at the same time, the velocity dispersion is increasing by a lot if you go to lower and lower metallicities. And then in this survey, there weren't that many stars with metallicities even lower. So they grouped them all in one bin, and there's quite large uncertainties on the points. We can see there's still some of this rotational signature, but it's a bit weaker than in the higher metallicity stars. And actually the velocity dispersion, if you compare it, is even higher than for previously. So this is where we were at with the more standard bulge surveys, mostly metal-rich stars. But then with PIGS, for the first time, we can do this as a function of metallicity for even lower metallicity stars. So we can do the metalpoor rotation curve as a function of metallicity. And here in this first panel, it's overlapping with in metallicity with one of the Argos bins. And we find here these models are for just a boxy bulge, so bulge that formed from the disk. And in this metallicity range, it still agrees quite well. Seems a little lower here, but I'll show later that this is probably an artifact from contamination. So this is consistent with the typical bulge surveys. So then if we go to lower metallicity, and this is actually where PIGS start to have more and more stars, we can see that the rotational signature is a bit lower than before, and the velocity dispersion is increasing. And we can see this even lower rotation in the next metallicity bin and a higher velocity dispersion, and even more so for the very metalpoor stars. So this is below metallicities of -2. We have a really high velocity dispersion of over 150 kilometers per second. And it's unclear in this panel whether there still is some rotation for the very metalpoor stars. So as I mentioned before, there could be some contamination from different sources. So what we're really interested in is the stars in the inner galaxy that stay in the inner galaxy. But there's also stars just moving through on halo orbits that just spend a short time in the inner bulge region and then go out back to the halo. So this is work in progress. We're looking at the distances and orbits of the pig stars. So distances are tricky because the bulge is quite far away, and the extinction makes it more difficult to use photometry to get good distances. So we're collaborating with the Starforce teams, Anke and Pristine to get distances using the Gaia parallaxes, pig stellar parameters, photometry, including a prior for a distribution of stars in the Milky Way. And these distances are really quite good. And we're combining this with the Gaia proper motions and the velocities, and integrating these in the Milky Way potential to get the orbits of the stars. And this is in collaboration with Giacomo Moinari and other people in Strasbourg. So here is a slice of this potential, or a similar potential that we are using. So this is X and Y, and the sun is here, and here's the inner galaxy, is the barred boxy peanut bulge. So if I then overplot where the stars in pigs are, you can see here the black dots. Most of them are really in this inner region, with a small contamination in the front and in the back. And on the right-hand side, I'm showing the same X coordinate, but versus the height above the plane. So all these stars are within about 2 kiloparsec of the galactic plane. And 90% of the sample is within 3.5 kiloparsec of the galactic center. So this is really a good sample of inner galaxy stars. So then what we can do is we can have a look at how many of these stars actually stay in the inner galaxy. So here's a figure that's showing the metallicity and versus the fraction of stars that is confined within a certain region. And here in red now is shown the stars that stay within 3.5 kiloparsec. And we can see that this fraction decreases as you go to lower and lower metallicities, meaning that the lower metallicity stars are actually mostly halo stars that are just passing through the inner region. And we can do this for different cuts in maximum distance. But another survey, which is the CEMP survey, they also looked at metalpoor stars in the inner galaxy. They had a much smaller sample, but they were already seeing this number of halo interlopers that is increasing with decreasing metallicity. But now we can see it at much higher resolution with many more stars. So then here are the same curves for stars that stay within 5 kiloparsec, which is for almost all metallicities, it's more than 50 or 60% of the stars. And then 80% or more of the stars always stay within 10 kiloparsec. So it's still very much an inner halo sample, even the stars that don't really stay in the inner, few kiloparsec. So here I showed this plot already before. This is the exact same plot. But what I'll show you in the next slide is the same thing, but only including stars that stay within 5 kiloparsec. So we're moving the stars that are really more like halo stars. And when I do that, you can see that things get a lot cleaner, first of all. This agrees better with the models. And here you have a very clean rotation curve that is decreasing as a function of decreasing metallicity. And on the bottom panel, which was the velocity dispersion, we can see if we flip back and forth, that the velocity dispersion is now much more equal between the different metallicity bins, because I am removing these stars on high apocenter orbits. And then I can do something similar, making an even more strict cut, let's say 3.5 kiloparsec, and it becomes even a little more clean. And I think what's interesting to point out here is that in the very metalpoor stars, the very metalpoor bin, here at positive longitude, we still see a signature of rotation. So these very metalpoor stars, which we might expect to just move randomly as kind of halo stars, They don't actually. There is still some coherent rotation, even in these very metal poor, these very old stars. So some other surveys using either different methods or smaller samples have seen something similar to what we're finding. So this is a survey led by Andrea Kunder, focusing on Aura stars, which are typically also quite metal poor and relatively easy to recognize. And in blue is what she defines as halo, which I think is stars that move, that don't stay within 3.5 kiloparsec. And on the right-hand side is the velocity dispersion again. You can see these blue stars have very high velocity dispersion, whereas the other two samples, which is the bulge, they have lower velocity dispersion. And then comparing here the rotation curves, you can see that the blue stars, the halo stars, they don't really show rotation, although this point might maybe indicate something. But these green stars, which stay in the inner galaxy, they have a nice rotational signature, although the magnitude is a bit lower than what expected is from the line here. And then here on the right-hand side is the same COMB survey that I mentioned before, which is metal poor stars. It's a bit more metal rich than PIGS, typically -1, -1.5. And they compare the rotation curve of all their stars, the stars that are not confined to the inner galaxy and the stars that are confined in the inner galaxy. They don't find a really big difference in the rotation curve, but again, a big difference in the velocity dispersions, which makes sense. So then what can we learn from this kinematics? So as we go from high to lower metallicity of metal poor bulge stars, we see a decreasing galactic rotation. But this is for the first time we're seeing that it's still visible even in the very metal poor regime. At the same time, as you go to lower metallicity, there's an increase in the velocity dispersion. And this appears to be largely due to interlopers from the halo that are more common at lower metallicities. So these things can teach us about the transition of bulge, which formed from the disk, to the halo, or a classical spheroid component. They also teach us about the formation of the boxy peanut bulge. There may have been actually very metal poor stars already present in the disk at early times that are now currently part of this structure. And this could explain some of the rotational signature that we're seeing. But then also this is dynamically a very complex region. There's also a bar in the Milky Way, and this has a very strong dynamical effect, and it could even spin up something that wasn't rotating in the beginning. So if you have a spheroid like the halo or something else, it could spin up under the influence of the bar. So at the moment, it's still not clear what these observations exactly can tell us, and hopefully more detailed chemistry will also help to pin down the origin of some of these stars. So this was the first topic on the kinematics, which hopefully we'll have a paper out in the near future. And the second topic is on carbon-enhanced metal poor stars and what we can learn from them about the inner galaxy and the galactic halo. So why are we interested in these carbon-rich stars? So we're interested in very metal poor stars because they're very old and they bring us closer and closer to the early universe. And we find that in the halo, in metal poor star samples, many stars are actually carbon rich. And the definition we're typically using is the carbon over iron abundance is larger than plus 0.7. So I'm showing an example here of a compilation of high resolution spectroscopy of very metal poor stars. As a function of metallicity, the carbon abundance. You can see that most of the stars are here around 0, where you would expect it. But then there's this big cloud of carbon-rich objects. And also over here. Actually, if you do the calculation, then you can find that the metallicity, for lower and lower metallicity, a larger and larger fraction of the stars is carbon-rich, until almost all of the stars in these metallicity ranges are carbon-rich. So these stars are apparently special. They tell us something about the early universe. So what do we know? What else do we know about these carbon-rich stars? So here I'm showing a similar plot, now metallicity versus absolute carbon abundance. So the carbon enhancement line is this one. And this is a compilation of carbon-rich stars, or CEMP stars. And we can already see that there's kind of 2 or 3 groups. There's this blob here at slightly higher metallicity and higher carbon abundance. And then there's the stars at lower metallicities. And it becomes even clearer when we color code this by their chemical abundance of barium, which is a slow neutron capture process element made a lot in asymptotic giant branch stars. So the stars up here are all barium rich, and the stars down here are typically not barium rich. So these are the CMP-S and the CMP-No stars. And what else we found out is that most of the CMP-S stars are actually in a binary system. They have radial velocities that are consistent with having a binary companion. And actually most of the stars, but not all of them in this category are in a binary system. And the fraction of binary stars among the other category is much, much lower. Although not actually, yeah, so it's lower, and it seems to be more consistent with normal, seems to be consistent with just a normal binary fraction in this group of stars. So what does this tell us about the origin of these stars? So these barium-rich CMP-S stars, they likely have received the carbon abundance that they have from a companion star. So this is the star we see today as carbon-rich, and at some point in its life, it was enriched by carbon and S process elements by a former AGB companion. So these stars were not born carbon-rich. But the CMP-No stars, on the other hand, they're not all in binary systems, so there must be something else. We actually think that they were born carbon-rich from the material from exotic processes in the early universe, such as a faint supernovae, where you only have the outer regions with the lighter elements being expelled and the heavier elements locked up. So this gives you a high overabundance of lighter elements like carbon, or asymmetric explosions, but also rapidly spinning stars, spin stars, really massive stars. They can create a large overabundance of carbon. And actually, it's not just carbon that is different in these stars. They have very peculiar abundance patterns in the other elements as well. So getting back to the binary fraction, here is the same diagram, metallicity versus carbon abundance, but now only stars for which we have radial velocity monitoring. So we know that they're either single or in a binary system. And again, this is the CMP-S stars, which is mostly in binary systems. But there's a few single stars, which are sometimes quite puzzling. So then the CMP-No stars, which are now shown in red, we have many more single stars, but still we have a large number of binary stars, which are the star symbols here. And actually in my paper in 2019, we compiled all the radial velocities and added some more for some stars, leading to this compilation. And we found that most of the really carbon-rich CMP-No stars are actually in binary systems. So the binary fraction here is much higher than the typical binary fraction among metalpoor stars. So this is kind of still, we don't know why. This doesn't mean that they have to have interacted with a companion, but if they have interacted, that makes it more complicated to interpret their abundances to learn about the first stars. We could learn about really, really metalpoor AGB stars and their chemical abundances, but it's more complicated than we thought it was before. So despite all these things, I think CMP stars are really interesting for galactic archaeology. They tell us about the early chemical evolution in an environment and about the binary fraction and the binary properties in a population. So what about the inner galaxy? So the inner galaxy, we don't know that many carbon-rich stars. So here is again the same compilation that I showed before. The circles are halo stars, and the red and blue stars were the only CEMP type objects we knew in the bulge for a long time. So several of these come from the SkyMapper EMBLA sample that I mentioned before, but they have a quite low fraction of these carbon-rich stars, not as large as we know from the halo. And actually, most of them don't have very high carbon abundances. They are just around or above the threshold for being carbon-rich. And this could actually be a selection effect in the SkyMapper photometric selection. So remember, they use a similar technique as Pristine. They have this filter that they use covering the calcium H and K lines. But here I'm actually plotting spectra of stars with different carbon abundances. And the orange star here has a carbon abundance of +2, which is quite typical for the really CEMP stars. And we can see that there's a big carbon band in this region. So if a star is really carbon rich, it has a lot of absorption in this filter, and it actually looks metal rich because there's a lot of metal absorption. So you would confuse it for a metal rich stars, and you would not choose it for your very metal poor follow-up. So it might be a selection effect against these kind of stars. So in Pristine, we're using a much narrower filter that is avoiding this carbon band. So we were hoping to be less biased against carbon-rich stars. However, we're also employing broadband photometry, which can still be affected by other carbon bands throughout the spectrum. So anyway, what about pigs? What do we find? So we can derive carbon abundances from our low resolution spectra. Here is an example. In gray, an observed carbon-rich star, and in blue, a carbon normal model. And you can clearly see this huge carbon band, CH band, around 4,300 angstrom. So we can easily recognize these stars from the low resolution spectra. So we have carbon abundances for about 1,900 very metalpoor stars in pigs. And what we find is 96 new carbon-rich stars in the inner galaxy, which is shown here as the black points. So this is a huge increase in what we knew before in the inner galaxy, going from about 6 stars to almost 100 stars. So for these stars, we don't have the S-process abundances, so we cannot classify them in the different categories based on the S-process elements, but we can see how they overlap. So for example, these stars, they largely overlap with these blue points with the CMP S stars. And these stars are likely to be CMP no stars. So we're actually doing some high resolution or higher resolution follow-up to learn more about individual stars. But what about the fraction of these carbon-rich objects? How does it compare to that in the rest of the halo where we studied these stars before? And the comparison is shown here. In green is the typical fraction that is often used for comparison in the halo, and in black is the fraction in pigs. So we can see it's actually much lower in these metallicity ranges than in the halo, although at the lowest metallicities it's compatible with the halo fraction. So how can we interpret this difference? So as with the SkyMapper, it could be a result of photometric selection effects. Here is a nice example of a really carbon-rich star, one of the first ones discovered. And you can see these huge bands of carbon in the spectrum. And they affect the colors of a star. So if you use any colors or make any color cuts in your selection, you're going to be biasing yourself somehow. And we've done some synthetic photometry to figure out where carbon-rich stars would be in our selection. And it's unlikely the full explanation. So there must be some other explanation still. So if there is a lower fraction of CMP no stars in the inner galaxy, this tells us something about the early chemical evolution in the building blocks, building the inner halo. And these kind of objects that occurred, that that were in place in the early universe. And it might be that there were actually larger building blocks contributing to the inner galaxy, which is what we think how the hierarchical formation works. And these larger building blocks have a faster chemical evolution than the tiny dwarf galaxies. And this could more quickly remove the signal of the first stars and mix it in with normal supernova leftovers. So maybe that's why you would still see them in the lowest metallicity range, like in pigs, but not in the slightly higher metallicity range. So if there's a lower fraction of CMP-S stars, this tells us something about the binary properties in a population, because these stars form through binary interaction. For example, there could be a lower fraction of binaries in the inner galaxy compared to the rest of the halo. And I think this is still a topic that we don't know very much about. Also, the binary fraction in dwarf galaxies. So I think we're going to learn a lot about this in the next few years, and this might shed some light on why this could be different between inner galaxy and the rest of the halo. So then finally, there's another problem or challenge in this, which is what about the literature fractions of CEMP stars? Can we directly make this comparison that we're making, and is it really fair, a fair comparison between the literature and our sample? So this is again a work in progress, and it looks like the comparison with previous halo fractions is a little bit complicated. So again, the typical fraction of CEMP stars that people compare to, which is from a compilation by Vini Placco, it's a compilation of high resolution spectra in the literature from many different sources. So it could be biased because in the early days of doing metalpoor stars, people were interested in these really extremely metalpoor stars, but then also in these peculiar carbon-rich objects. So it may be that these samples are actually biased towards carbon-rich objects, and they have more carbon-rich stars than they're actually representative of the galactic halo. And then secondly, I've been studying the CEMP stars in different samples in the literature, from high resolution to samples of low resolution spectroscopy. And actually the CEMP stars in these different samples are quite different. And here I focused on only giant stars, because in pigs, we are only observing giant stars. So here we have, as a function of metallicity and the carbon abundance in this Placco high resolution sample. And we can see that most of these CEMP stars, now I'm only showing the carbon rich objects, they have really high carbon abundances between 1.5 and 2.5. And that is shown in the histogram down here. And then when I overplot the pig stars, which I showed before, we can see that actually most of the CEMP stars are in this range, between 0.7 and 1.5, and there's not that many here. So this is again what I showed before, that we seem to have this lack of really carbon-rich stars and a lower fraction of them. But then what do we see in other low-resolution samples? So here I'm overplotting the SDSS low-resolution sample of carbon-rich stars. And we can actually see here in the histogram, they also have most of the carbon-rich objects between 0.7 and 1.5. And they have some at high carbon abundances, but actually not that many relatively, if you look at the histogram. So the distributions of CEMP stars are actually quite similar in pigs and SDSS. And then you can plot it for a bunch of other samples from different low resolution surveys. But looking at the histograms here, almost all of them have most of their carbon-rich objects relatively low in this diagram, and they don't have that many up here. So it looks like the CEMP stars are different in high-resolution compilations compared to low-resolution surveys. So it might not be fair to compare them directly. And then finally, the carbon abundances have different trends in the different samples. So here I'm showing the metallicity versus the carbon abundance. And here is the average trend in this high resolution sample. So we can see the carbon is slowly increasing if you go to lower and lower metallicities. And the Pig's trend is very similar. So they're very much in agreement. But then showing the SDSS stars, we can see there's actually in the higher metallicity range, there's an offset. They have on average higher carbon abundances. And this is again similar for various samples. The details here are not that important. It's just showing that different samples have different levels of carbon abundances. And almost all of these, except the pigs, are halo samples. So they should all be similar. So this may be an indication that there's actually a role of the spectral analysis pipeline that produces different carbon offsets. And this can make comparing the CEMP fraction in different samples complicated. You cannot directly compare if the carbon abundances are not on the same scale. So I think that CEMP stars are really great probes for galactic archaeology if we can interpret them properly. And I think there's some work to be done here. But they're really good probes of first stars and early chemical evolution and binary stars and their interactions. So to go back to the big picture, in this talk, I've been talking about the buildup of the ancient inner galaxy, looking at metalpoor stars in this region. And I'm also interested in the properties of the descendants of the first stars, especially these carbon-rich stars throughout the halo and in the inner galaxy. And I think it'll be very interesting to compare the properties in these different environments, because these stars were likely born in different environments in the early universe. And in the future, we'll learn a lot more. There's a lot of ongoing and upcoming data so combining pigs with Gaia, and then the large spectroscopic surveys of Foremost and Weave in the Northern Hemisphere. And they will produce a load of data in both the halo and the galactic bulge. And I'm really excited to see what we can learn from these in the next few years. So to conclude, I've presented you the work in the Pristine Inner Galaxy Survey, or PIGS, which is a unique survey of metalpoor inner galaxy stars. The kinematics show us that there's a slower galactic rotation and a larger halo contribution for metalpoor stars. Then on the chemistry side, we found a low frequency of CEMP stars, but we're still unsure how exactly to interpret this. And then finally, I think that the near future for galactic archaeology with metalpoor stars, and especially in the inner galaxy, looks very promising. So thanks.
Thank you very much. It was a very interesting talk. And now I'll open for questions. Please, Maria.
Yes, thank you very much for this wonderful talk. Thanks a lot. I have some questions. One is concerning the initial candidates that you were considering for pigs. Maybe I don't fully get it when you mentioned this, but when you choose your metalpoor candidates, you were only considering the position of the stars, or what else?
So we are just going back here. Yeah. We're using the photometry. So we're using this color diagram. So we have the color, just a general temperature sensitive color on this axis, and then this metallicity sensitive photometry in here. So basically we make a cut and we only select stars in this region of the diagram.
Okay. I understand.
So that's how we select the metalpoor candidates. Yeah.
Okay. And then I have another question concerning that you mentioned that the models predict that the metalpoor, the oldest stars would be concentrated in the center, and this is only because the way they were formed initially?
Yeah, I think it's related to the hierarchical formation of the Milky Way. You have the biggest things that end up in the inner regions of the Milky Way, and these are the first to start forming stars.
Okay,
so that's where you get the very oldest stars.
So for this very first population of stars that were very massive, then the next generation that is actually the one that survived, you would expect them to be concentrated at the center.
Exactly, yeah.
Okay, I see. Then I have another question related to the metallicity tracers that you use, actually, is there a way that there is some process, exotic process, let's say, that is actually like deceiving you, like maybe the metallicity, the tracer that you are using for measuring the metallicity actually is not an indication that the star is old? Do you know what I mean? Is it clear?
I think maybe, yeah. So I guess you're asking, can you have a young metalpoor star? Or...
Yes, exactly. Or maybe if the way you trace the metallicity is like two ways, for example, that are different, so you can be sure that you are not missing something in the middle. Like, yeah, this is not really an old star.
Yeah, so I think we can measure the metallicity very well from the spectra. So I don't think there will be any confusion about whether a star is metalpoor or not. But of course, it doesn't directly connect to the age. You can have some metalpoor stars of different ages, and I think that's connected to the environment they were born in. So this is again the you can have very small dwarf galaxies that at a later time in the universe still form quite metalpoor stars.
Yeah. I see.
Yeah.
So so you need actually to have the whole picture to say, yeah, actually these are old, not just.
Yeah, so it's difficult to measure the ages of stars directly, but I think having more detailed chemical abundances tells you a bit more about the environments the star was born in. So that might help. Yeah.
Okay, thank you.
Thank you.
Elvis?
So, hi, Anke. Thank you very much for your talk. I wish to ask something that you mentioned before about the orbits and the range from the galactic nucleus that you are considering. Have you used the axisymmetric potential for the orbit integration?
No. So this I think this is yeah. So this is here showing the part of the so basically the XY projection of the potential, and there is the bar in the potential.
Oh, it's XY. I thought it was X. Okay, all right. But is it time varying or something?
I think so. So I didn't do the orbits. It was Giacomo, but I think there's some pattern speed of the bar assumed in the model.
Oh, great. I was just about asking that because I spotted some differences using the MW 2014 potential that Galpa uses, for example. And adding a bar really makes the churning effect and makes the stars go all over, making the bands, the resonant bands, and etc. But very good. So your study considers a rotating bar, and it's awesome.
Yeah. We don't know how well it's working because the uncertainties on the distances are still quite large. So we were looking at the stars as a distribution and not really saying this individual star is doing this or that.
Mm-hmm. Okay, I think that's it. Thank you very much.
Well, I also have a question about those carbon-rich stars that are not binaries. Is it possible that they have a lost AGB companion? Because I've been reading some papers that are looking for lost companions in Gaia through Gaia proper motion and parallax data, and they're finding a lot of candidates. So could it explain why you can find that much non-binaries?
So I don't know what the process would be to break up these binary systems, but it's not just the binary, it's also the difference in the chemical abundances. So you clearly see in these two different categories, so the the CMP no stars, they don't show this S process enhancement, which would be typical for interaction with an AGB companion.
Mm-hmm.
So that's another reason to say that they likely didn't form from binary interaction, because they don't show that signature.
Okay. Oh, sorry. Okay. Do we have any more questions here? Guilherme?
Hi, Anke. Hi, Larissa. Larissa, I have a bunch of questions. Would you like me to ask after we finish the transmission, or now, because we are on time?
I think you can start asking now. If if we go too much after 3:10, 3:15, then I'll ask you for stop the transmission. Okay.
Okay.
Go ahead.
Hi, Anke. Thank you for the seminar. I think it was quite clear. I actually saw once you talking about this work on the Gala Science meeting, and then I had to invite you to expand on this because I find it fascinating. The first question that I have is regarding the potential as well, because the fractions of stars that reach, for instance, stay within 3 or 5 or 10 kiloparsec from the galactic center will depend on the pattern speed of the bar. So I don't know if you tested this, but variating the pattern speed of the bar could change these fractions. Of course, the qualitative results should be the same, of course, but maybe changing the pattern speeds of the bar might provide some, I don't know, maybe for those of you who are interested in doing models of the galactic center, for instance, this could be useful information for them. I don't know if you tried that.
Yeah, so we haven't tried varying the pattern speed. We have tried varying the strength of the bar a bit, and the results don't change that much. So there might be little variations, but qualitatively the results are similar.
Yeah, I see. And using Star Horse distances for this task is perfect, actually. I think it is great that you were able to use the stellar parameters from your low resolution spectroscopic survey to determine the precise distance with Star Horse. I think it's perfect, and it's beautiful to see like the transition from the rotating signature to the like crazy motions of these the most metalpoor stars. And the other question that I have is also regarding the CMP fractions, because you told us that you can utilize the new distances that you determine using Star Horse in order for you to integrate the orbits, and then you can like validate which stars stay within the inner regions of the galaxy and those that are just interloopers. So can you actually utilize this method in order for you to separate from your carbon enhanced, from your CMP stars, those that belong to the halo and those that belong to that truly belong to the inner regions of the galaxy, in order for you to have like an updated fraction of CMP stars as a function of metallicity? I think that might even enhance the signature of this difference between the CMP fractions from Paulo 2014. I don't know. I think it's 2014, and those from the inner regions. Maybe you tried that.
Yeah, it's definitely something we've been thinking about, and I should really do that. But something that's been keeping me from that is knowing that the photometry of carbon-rich stars is impacted by the carbon bands in the spectrum, and we're using the photometry to get the distances in Star Horse. So I think for the very carbon-rich stars, the distances may be biased because of the photometry that we use, and also there's some issue in the spectroscopic parameters, and especially the surface gravity, which is difficult to determine for these really carbon-rich stars.
I see.
So this all plays into the distances that you get and then the orbits that you get.
I see.
So I will look into this, but I don't know yet how much we'll be able to trust it.
Yeah, I have no idea. But now that you said that the depth of the carbon bands might impact on the photometry, I think I haven't thought about that. But if you're using just broadband photometry, I think you show that you're using WISE and 2MASS and I don't know what else. But if you're using only broadband photometry,
also using optical photometry, which I think is more constraining. So the GEIR.
Yeah, if you're using broadband photometry, I don't know if this would impact too much, but I think it's a concern that I haven't thought about. Thank you. And the other thing that you showed is when you compare the different carbon fractions from the different low resolution samples. I think can you show that again, because I was actually worried about that. Not on your work,
This
but
one?
worried on the work from our side. Yeah, exactly this one. Because, for instance, the U1 2020 paper, it's actually processed with the NSSPP as well. So, and it's different. Yeah, it has been reprocessed with the NSSPP for the paper by January. And then it is different from the paper from Placo 2018, which is different from Chunk 2021, which is a compilation between Placo 2019 and my own paper from last year. So I think I am kind of worried that the fractions of carbon, the behavior of the carbon abundance as a function of metallicity is so different between these samples, because they should be the same, because they have been analyzed with the same pipeline.
Yes, exactly. Yeah, so I'm actually writing a paper about this now, which should be out very soon. So just pointing out that even comparing different low resolution samples in the halo, we're not getting the same answer.
Yeah, I see. Yeah, it actually makes me kind of worried, but yeah.
I've been having sleepless night about this, so yes.
Yeah, that's why I hate CMP stars. Okay, I guess that's it, Anke. Thank you so much, and maybe we can discuss something else after we finish the transmission. But those were the real questions that I would like to ask about the presentation. Thank you so much.
Thanks.
Well, thank you again, Anke. We're stopping the transmission from YouTube. Do you have anything to say before we cut the transmission?
Just thank you very much for having me.
Okay, so Richard?